maybe you have seen The Three-Body Problem. It's a show on Netflix. It's kind of popular right now. It was a book. The book was pretty fun. It's a series of books. And I want to show you all of the details it takes to model the three-body problem. So this might be a long video. I don't really know. We're just going to plow through it. We're going to do it live. We're just going to do it. So this is a symbol from the show, the three-body problem. The three-body problem is essentially how do we model the motion of three objects that all gravitationally interact with each other? And the answer is there's no solution, no analytical solution for that. There's a bunch of stuff to get here. We're going to start off with a two-body problem. I'm going to tell you about the two-body problem. We're going to model the two-body problem, and then we're going to convert it into a three-body problem in Python. We're going to do all of that stuff in Python. It's going to be great. Well, I'm going to have fun. It might not be great, but you got to stick through this stuff if you want it anyway. So the first thing is, how do we model the motion between two interacting gravitational objects? So imagine I have object A and object B, and they have vector positions RA and RB. I can find a vector from A to B. I'm going to call that vector RAB because it goes from A to B, and it's just going to be vector B minus vector A, RA. And then I can calculate the gravitational force on A with this equation, G. That's the gravitational constant. It's just a small number. Product of their masses, the mass A times mass B, divided by this distance squared. So that's the magnitude of that vector squared. And we're going to do all that in Python. And then this is a unit vector. This is a vector of magnitude 1 in the same direction as RAB. And this way, it'll give us a vector force. And that is kind of important. Okay, so let's just talk about the two-body problem really quickly because this one is solvable. I'm not going to solve it. I have a video for that down below if you want it. But imagine that I have two objects in space and they're interacting with each other. Well, the first thing to realize is that if I locate both of these in 3D space, then I have 3 coordinates for this object and 3 coordinates for that one. So that's 3 plus 3. That's 6 degrees of freedom. So that's kind of a bit. But it turns out that we can reduce this to something that looks like this. This is the center of mass, and this is the reduced mass. And if I only have to locate the location of the reduced mass, one of the objects you can think of it, with respect to the center of mass. So suppose there's a center of mass right here, and I make the center mass stationary. If that's the case, then I actually only need 3 coordinates. So this is 6 degrees of freedom. This is 3 degrees of freedom. I can represent it that way. Now I can get to 2 degrees of freedom with this by saying that if angular momentum is conserved, and it should be, then I can confine the motion of this mass into a plane. We could put this in the XY plane, and so it wouldn't be in the Z plane at all. No matter what happens, it's going to stay in the XY plane. So now we're down to 2 coordinates. And finally, by using a potential that only depends on R, when we do some math here, we'll get to a 1 degree problem, and where we can model this just as the distance from the center along with some other essentially fake potential. And then you can get it to 1 degree of freedom, and then that is solvable. You can solve that motion. We're going to do that with 2 objects in WebVPython, which I'm going to show you in a bit. But in order to do that, we need some initial conditions. So let me just go ahead and make the objects in WebVPython, and then we'll do that. So I'm going to make 2 objects. I'm going to make spheres, and I'm going to put these spheres, and then I'll show you how to model them. So I'm going to have, let's say, B right here and A right there. They're going to be different masses. I don't really care what they are. I'm going to call this RA and RB, and I want the center of mass to be at the origin just to make things easier. So if that's the case, and this has a mass MA, and this has a mass that's MB, and this is MA, then RA MA, that's just a scalar value, would have to be equal to RB MB. So once I pick these masses and that, I can find RB. So let's draw 2 spheres on the XY axis, and then we'll talk about what their initial velocities are, which we'll have to derive that too, because I want them to behave. I don't want them to be crazy. And then I'll show you how we model the motion of it going forward. numerically, which we don't have to do. We could do it analytically. Okay, jumping over to WebVPython. Here we are. Okay, if you haven't seen this before, WebVPython is like Python that has built-in modules for displaying things in 3D. It's pretty awesome. I've already put some constants in here just to get things started. There's my gravitational constant G. This is the mass of our sun approximately. This is AU is the astronomical unit, just so we can have some spacing size. And this is not the radius of our sun. I put it a little bit larger just so we could display them. So let's just pick. I'm going to pick RA. So let's say RA is equal to 0.1 AU. Okay. And then I can pick MA, the mass of star A. It's going to be just the mass of the sun. And then, let me make that a little bit bigger. Feels a little bit better. Now I can pick the mass B. I'm going to make it a little bit lower mass. Mass B is going to be 0.8 times MS, so smaller. And then I can use that to calculate the location of RB. RB is going to be equal to RA times MA divided by MB. Now we can make these two spheres. So let's call that first star SA for star A. It's an object of type sphere. I'm just going to type sphere just like that, and I'm going to run it. Okay, because sphere is a built-in function in WebVPython, and once you call that, it will create a 3D environment that you can see the sphere in, and you can manipulate it. So let's see what that looks like. There's my 3D sphere, and I can indeed rotate it around with a right click. I can zoom in and out with the scroll, and there is lighting and stuff like that. So that's kind of cool. So you can kind of see where we're going if you haven't played with this before. I'm going to give you a link to the code in the description down below, so if you want to play with it, you can. And it's free. Okay, so the sphere object has parameters that we can give to it. We can give it a position, a radius, a color, and things like that. So let's give it those objects. So the position is going to be a vector. Vectors are a built-in class in WebVPython. And I'm going to put it RA on the x-axis, 0, 0. Let's give it a radius of RS. So radius is a predefined property of the sphere. So I'm not just making this stuff up. Color equals color.yellow. And then let's put the other object, SB. It's a sphere. Its position is vector. It's going to be on the negative x direction. So negative RB 0, 0. I calculated that as a positive thing. It's going to be the same radius, just so you can see them better. And let's make this one cyan. Color equals color.cyan. I'm going to run it. Okay. So I need to give some other properties of my stars, in particular their initial momentum. So I want these to orbit in a circular motion before I add my third star, and then we can change that just so we can get things behaving to begin with. So I want to give star A an upward momentum and star B a downward momentum, but I need their velocities. And I want their velocities so that they're moving in a circle. So let's find the circular motion for these two things. Okay, if I have their positions and I want them to move in a circle about the center of mass, what would their velocity be in order to do that? So I need to switch back over here to paper. Paper time. Okay, so here we have, let's draw a picture. There's our center of mass. Here's object A. It's going to be going this way. Here's object B. It's going that way. But they are moving in circles around the center of mass. And so in that case, I can calculate the velocity by finding the gravitational force, which points towards the center, and using the definition of centripetal acceleration. So I can say that the gravitational force, I'll call it Fg, on this A right here, is going to be ma va squared over r. mv squared over r is the mass times acceleration for moving in a circle. And this is going to be the gravitational force. Now, we have to put in our values here. So for the gravitational force, I'm just dealing with the magnitude here. I'm going to say this is equal to G, mass A, mass B, and the distance between them, this is RA, and that's RB, so it's going to be over RA plus RB quantity squared. So that's the gravitational force. And then over here, I get MA VA squared, and this is the circular radius. You'll notice that's just RA, right? It's moving in a circle of radius RA. And now I want to solve for VA. That cancels. I'm sorry. And I get VA is going to be the square root of G mass B RA divided by this, RA plus RB. Right? It's squared. I could put in the square root, but it came out 2. So now I can calculate what that would be, and I can give this that momentum. PA is MA VA, where it's going to be in the y direction. And then I'll give this one a velocity. I'll just make this momentum the opposite of that so that the total momentum is 0, so the center mass stays constant. Okay, so let's just put that in. It won't display anything, but let's switch back over here and do that. Okay. So I'm going to calculate this stuff down here. So let's calculate this VA. I'm going to call it VA. I'm just going to type in my equation that I just typed right there. Square root of G times MB, no, I did MB, that's right, times RA divided by RA plus RB. That's it. Okay, and I don't even need to know what that velocity is. But it's kind of hard to just intuitively pick values for those things. But I can now use those to give momentums to both SA and SB. And I'm going to give them as a property of the object. SA dot P, so that's the P dot P is the momentum of the object SA. It's just going to be equal to MA times VA times the vector. I do want it to be a vector, 0, 1, 0. So it's going to be moving in the positive y direction. Now for the other momentum, SB dot P, I'm just going to say it's equal to negative SA dot P. So now the total momentum is 0, and that means the momentum stays at rest. But now I have their momentums, I have their positions. How do I know where they're going to move in the future? Well, now we're going to do a numerical calculation. Okay, so let's switch back over to the paper. I told you this might take a long time, but we're in it till we win it. We're in it all the way. Okay. So let's just draw a little picture here. Here's my coordinate system. Here's object A. Here's B. This one's moving that way. This one's moving that way. As they move, their positions are going to change relative to each other, so the gravitational force is going to change, at least as change in direction. And normally we could use momentum principle, which says F net is the derivative of the momentum. And that's kind of hard because these are all vectors and the momentum's changing direction. Everything's complicated. But what we can do is to pick something like delta t is 1,000 seconds. I think that's what I'm going to use. So in 1,000 seconds, this is not going to move that far. Maybe it moves, just right here. And if it moves a very short distance, we can assume this force is constant. So I'm actually going to calculate that force. I already showed you how to do that with the gravitational force. Once I calculate the net force and assume it's constant, I can write this as F net for, I'm just talking about object A. It's going to be the change in momentum of A with respect to t. So I'm going to write it as a difference, right? This is true if the net force is constant. I can write this as a difference instead of a derivative. And if the delta t is small enough, this will work well enough. And this would be, I could write this as P2 minus P1 over delta t. So P1 is momentum at the beginning of the time interval. P2 is the momentum at the end of the time interval. And if I multiply by delta t, I can solve for P2. P2 P1 plus F net delta t. So I can find the new momentum at the end of that time interval with this. I need to know the initial momentum, calculate the force, multiply by delta t. Now, once I know the momentum, I can use that to find the new position. So the average velocity is the average momentum over the mass. Right, momentum over mass is velocity, and that's going to be the change in position with respect to time. Again, I can write that as a finite difference. So this would be R2 minus R1 over delta t. And then if I solve that for R2, I get R2 equals R1 plus P over M delta t. So this is my numerical solution for solving the two-body problem, which again, you could do it, you don't have to do it this way. So what we're going to do is to calculate the force on object A based on the gravitational force, use that to update the momentum, use that to update the position. Do the same thing for object B, calculate the force, which is the same, update the momentum, update the position, and then move to the next time interval and do it again and again and again. Okay, so let's do this in Python and for two bodies and see if they do indeed move in a circle, and then we can add our third object and make the three-body problem. Back to the computer. Hello, computer. Okay, so I do need some things here. I need the time. So t equals 0, and dt equals 1,000. I did 10,000. So let's do 10,000 seconds. And we can always change that, right? What's a small time interval? Well, it depends on what's moving and how those things change and how accurate you want to be. This is something that we can change. But let's just leave it at 10,000 for right now. Now, in order to repeat the time interval calculations every time, I'm going to use a while loop. Let's use a while loop like this. So in Python, I can say while t less than some time. I'm gonna keep increase my time value until I get to something. And how much is it going to be? And let's just do 500 time steps. So 500 times dt. In Python, you put a colon there, and then everything that's tab indented is part of that loop. Now, I'm going to add another statement in here, rate 100. Since we're going to be animating these objects, rate tells Python, WebVPython, how many loops to do per second. It says don't do more than 100 loops per second. And so this is a way to control the animation rate. I don't want to have it run in real time because it would take too long. So I'm just going to pick a value that I like. That's it. Okay, now since these objects are moving, the very first thing that we need to do is to calculate that vector from A to B. And I'm going to use some specific notation to keep track of things because we're going to have to do this 3 different times once we get to 3 objects. I'm going to call this RAB as the vector from A to B. So it'd be SB.POS minus SA.POS. And if it's capital A, you have to say A. If it's just normal A, you say A. Okay. So that's that vector. Now with that, I can calculate the gravitational force I'm going to calculate the gravitational force on A. So I'm going to call F A, I'm going to call BA. So this is the force that B exerts on A. That's just the notation I use, and it's probably not the best, but you pick something and stick with it. So you don't always have to think about things, and you can make things work a little bit better. So this is going to be the gravitational force G times MA times MB. I'm just using that gravitational force equation times the norm. Norm gives me the unit vector for that vector. So it's a built-in function in WebVPython. Norm RAB. Now, I got those backwards, right? This is the force on A, but it's the vector from A to B, so it's pointing in the direction of the force. And then I need to divide by the magnitude of that, mag RAB squared. So that's the gravitational force on A. Now I can use that to update the momentum for object A. SA.P equals SA.P plus FBA times dt. That's the same equation that we had before. You don't see the indices because this is an update equation. This is a make equal to equation. It takes that value and changes it. So we don't have to worry about the indices. Now what about object B? It's going to move too. We could recalculate the force, but there's no point. Because object B has an equal and opposite force for object A. That's the same interaction. So we can just use the negative for that one. So SB.P equals SB.P minus FBA times dt. Now that I have updated the momentums, I can update the positions. So let's update the position of object A. SA.POS is SA.POS. And this is like the RA, right? Because it's an actual object, so we're going to use its position as its vector location. Plus SA.P times dt divided by MA. And then the same thing for B, SB.POS. SB.POS plus SB.P times dt divided by mb. And then I need to update time, or your loop will run forever. T equals t plus dt. Let's see if it works. Yeah, I might have made a mistake. I made a mistake one time. Remember that one time I made a mistake? Let's see. So let's save it, because you never know. Save. Run. Okay, there you go. Looks pretty good. Pretty happy. Now, let's make it a little bit better. I'm going to make a little trick up here. I'm going to go, when I define those spheres, over here, I can add another property. Make underscore trail equals true. So this will attach a trail to that object, and when it moves along, you'll leave a trail behind, which is kind of cool. And you can make the trail a certain length and all sorts of properties. You make a dot or whatever, but this is do the normal make trail equals true. Now let's run it. So there's my two-body problem. You'll notice that the center of mass is at the center, and it doesn't move because the total momentum of the system's 0, because they have equal and opposite momentums. But I mean, that's pretty awesome. And this is in a plane, right? That's what we said for the two-body problem. Okay, so we have a two-body problem. Now we need to do the three-body problem. So the three-body problem is the same thing, but I have 3 objects. So that means I'm going to have to calculate 3 gravitational forces, and I'm going to have 3. Each object has more than one force on it. Let's just do it. I mean, I could do it on paper, but I think that's the same idea. So let's just go ahead and make star C. I'm going to put it, just to make things work out for now, and we can change it later, I'm going to put it on the z-axis, and I'm going to give it a mass. I'm going to pick something. I'm going to give it no momentum. That way, I won't have to change the momentum of those 2 objects, right? Because if I had a momentum, in the x or y direction, I have to adjust the momentums of those, which is possible, and we can play around with it, but we just want it to work first, and then we can mess around. So up here, let's go ahead and add a third star. What should we call it? Oh, let's call it SC, right? That makes the most sense. Position is going to be vector. Let's put it at 0, 0, RA, right? Same kind of distance. And then it has the same radius, RS, and then it has a color, color.magenta, and then make trail equals true. We know we're going to make it move. Now down here, I need to give it a momentum, so it has to have a momentum, even if that momentum is 0, because it's a vector. So sc.p equals vector 0, 0, 0. And we can, like I said, we can change that later. We're starting off with some values there. Now we have an option. I do want to go to paper real quick here, because how do we draw these, how do we calculate these 3 vectors and these forces that we're going to have to deal with? So I have A, B, C. I calculated this, R, A, B. Now I'm going to calculate this vector, R, B, C. Notice my convention. This is from A to B, from B to C. And this one I'm going to do from C to A, so R, C, A. And then when I calculate the forces, the force of B pushing on A is going to use this. And the force of A on B would be the opposite. So each planet, each star is going to have 2 forces acting on it. Okay. So let's use that convention to find our things. And it'll help us keep track of everything. Now, if you have more than 3 objects, there's other ways to do this. You can make a list. You can make a list of objects so you don't have names for them, and it'd be much simpler, but this is fine here. So now I can just follow the same convention here, right? I can say RBC is SC.POS minus, not equals, minus SB.POS. RCA equals SA.POS minus SC.POS. And now I need to calculate 2 more gravitational forces. So right here, I'm going to say F BC, so it would be CB, is going to be G times MC times MB times norm, and that vector that I'm using right there is BC, RBC, divided by mag, RBC squared. And then I need one more force, and that's going to be FAC. It's going to be G times MA times MC. Did I give C a mass? I did not. So let's put it up here. MC equals 0.5 times MS. Again, just making up stuff here. You can change that. Norm RCA divided by mag CA squared. So now I have my three forces. Now each object has two of those forces. So what I'm actually going to do is to set a property of the star as the net force. So I'm going to say SA dot F is the net force on F and on A. So here I know this one, it has this one right here, FBA. What's the other force on it? Well, it's FCA, but I have FCAC right there. So since it doesn't end in an A, that means I have a negative FAC. And then FB dot F is going to be, I'm looking for the B's. Here's one, but the B's in the front, so it's negative FBA. And then I have this one plus FCB. So you see how I'm kind of like keeping track of my complicated system with my notation there. FC dot F is going to be negative FCB plus FAC. Yeah, got it. Okay. So now down here, instead of the force of A, I'm just going to say FSA dot F. Here I'm going to say SB dot F, and I'm going to say plus, not minus. And then I need to do the same thing for C. SC dot P equals SC dot P plus SC dot F times CT. And then down here, this is fine, that's fine, but I need one of these for C. So SC dot POS equals SC dot POS plus SC dot P times GT divided by MC. Whew, do you think it's going to work? I don't know. Let's find out. Let's save it and run it. Something happened. See, typo, capital CA. Where did I have? Can't find variable CA. I just left off the R. That's what I think I did. Maybe I made that mistake on purpose. There it is right there. Okay, there's your three-body problem. It's pretty. Okay, now that what happened right there? That's important. So you can get a explosive event like that, because what happens when these objects get really close together? When they get really close together, then our assumption that the force is constant over that time interval isn't always a good assumption. Now, we can fix this. We can fix this a couple ways. Number one, we can make a smaller time interval. Let's make a smaller time interval and see what happens. So down here, I'm going to make this 10 times smaller, but that means I want to make this run 10 times faster. And let's make it run longer. I just put 900 because I don't want to type twice. And let's see what happens here. It stopped. Why did it stop? I made because I made dt smaller. Right, so it only ran for, so I do need to add another thing right there. Okay. Now, you see it's not exploding. And that's cool. There's your three-body problem. This is why, spoiler alert, this is why they left. Okay. So there's your three-body problem. And it's kind of artistic, and I'm pretty happy with that because I love that right there. That's going to be my thumbnail. Right? There's your thumbnail right there. Three-body problem. Yeah. So let's just think about some things that you could do. Homework for you. You can take the code. Verify that energy is conserved. So calculate the kinetic plus potential energy for the system and see that it's constant. That's a lot to do. It's not terribly difficult. You can even plot the energies as a function of time and see if they're constant. What about momentum? That's a little bit easier. So you can plot the x momentum of all three objects plus the total and show that it's constant. You can plot the angular momentum and show it's constant. These are all things that say, hey, it's working, right? That's a check. Now, the fun homework is to try to find stable orbits, stable initial values for which you can have things move and behave. And there are some. Now, hint, put all the masses the same. It's going to make things a lot easier. There are some, even the ones that I have, if I have the two masses right here and the mass right there moving this way, I think that might be a stable system, but it'd be kind of fun. So play around with that. You know that you can just change the initial conditions. You cannot break the code. Don't worry about it. If you go to the link down below and you edit it, it doesn't save it, but if you want to save it, log in and make your own copy. So that's the three-body problem. Hope you enjoyed that. I'll talk to you later.